Alright, so my project was attempting to, as accurately as possible at least, determine NBA player archetypes or playstyles present in today's NBA. So the motivation behind this project and kind of the problem statement for me is, to me, there's not a lot of good, neither helpful nor accurate data science in the NBA. And a lot of the related works, especially I noticed this in, a lot of this stems from poorly chosen data. And to me, there's too much focus on traditional and widely used advanced stats in current data science in the NBA, and not enough focus on stats that actually show how a player plays or the tendencies a player plays with. And to me, at least, if I can successfully model how the players play within a game and interact within the game, this makes it much more straightforward to accurately simulate individual games and thus project seasons more accurately. So my data consisted of 4 datasets I web scraped from NBA.com. I did decide I would use the traditional and advanced stats similar to related works, but I'd also use data that represents the player's playstyle and tendencies more so. And this was shooting location data and touch data. So this data consisted of basically the distance on the court from the hoop that a player made or missed a shot from. And then the touch data had data like how many times the player touched the ball in general, how many times the player touched the ball in certain regions of the court, and stuff like that. I next did some data cleaning and exploratory data analysis. After doing a heat map as part of my EDA, I noticed there were some features that were very highly correlated with each other, and this was not super surprising. When I looked at those features, I did use some domain knowledge to decide to drop them, and the features I decided to drop were mainly percentages of a calculation of two or more other features. So for example, and this was especially apparent in the shooting data, I dropped field goal percentage because I already had field goals made and field goals attempted, so field goal percentage was not giving me a whole lot of useful information. I also removed players altogether if they played less than 50% of the team's games or played under 15 minutes per game. There weren't many missing values in the data, and those that were missing I entered as 0, because if a value was missing, it likely meant that the statistic wasn't necessarily applicable to that player, simply because the player did not perform that certain action enough. So after I got all my data and merged all my data sets and dropped the features I wanted to, I still had about 74 features. So I definitely needed to reduce dimensions quite a bit. So I chose to use PCA because it effectively reduces dimensions of high dimensional data while still retaining a good amount of information. Also, I did not necessarily need to be able to interpret what each component meant, because I solely needed to reduce dimensions in order to cluster. And then after clustering, I could merge the cluster information back with the original data, thus giving me all the information I need, which is also interpretable. And as you can see from this chart, I ended up choosing 12 principal components because it retained about 85% of the information, and that was my overall goal. Alright, so this is a visual representation of the top 3 principal components after I did PCA. Obviously, I just said I chose 12. However, I can't have a 12-dimensional graph, so I decided to help visualize it with just the top 3. This only retains 56% of the information, but again, it's good for visualizing what is happening, maybe with more dimensions. So after PCA came time for clustering, and I chose the number of clusters to be equal to 10. I based this decision off calculating the silhouette score. The silhouette score is basically the how similar an object in a cluster is to other objects in the same cluster versus how similar it is to objects in another cluster. And the maximum silhouette score is the ideal number of clusters to use. So I knew I wanted at least 10 and at most 15, so I calculated the scores for n equals 10 to n equals 15, and it turns out the max was at n equals 10. So I used 10 clusters. And I use k-means because it's a quick, simple implementation that's easily understandable, especially in this context. Also, k-means is very good for large data sets and high-dimensional data, which is what my data set is. And in the future, I might look to a more advanced form of clustering, as k-means does not cluster outliers that well. And there are plenty of outliers in this kind of data, but they're outliers that I need in this kind of data to learn what I want to learn. So this is a similar visualization as I just showed with the principal components. However, now the players are colored by cluster. So you can definitely see, especially from the zoomed out kind of version, you can definitely see some very distinct clusters of players within this data. And again, this isn't the 12-dimensional data that I'm using for the real model, but again, I think this is a fun way to kind of visualize what's going on. As you can see, these are all the clusters. So one issue I ran into after clustering was doing the cluster analysis in a smart scientific way. Cluster analysis consisting of simply looking at the stats of players within each cluster proved to be much too cumbersome, with 74 features within each cluster and anywhere from 20 to 30 players. So I decided to perform a form of multi-class classification so I could get the coefficients of features used in determining each cluster and thus the feature importance. To do this, I simply broke the multi-class classification problem into 10 binary classification problems. So I made 10 logistic regression models, each one implementing the one versus rest strategy. Essentially, this is making a logistic regression model to classify players in cluster X versus not in cluster X, and I did this for each cluster. As seen in the accuracy chart right here, every cluster had a classification accuracy of over 90%, except clusters 8 and 9. So it seems like those were more inaccurate clusters, if you will. So doing this classification did allow me to get the coefficients of each feature, contributing to predicting the cluster a player belonged to, and thus I was able to easily determine the feature importance in determining clusters. So getting to some results here, I titled Cluster 0 High-Level 3 and D Players. Some key characteristics for these players are great outside shooting, good defense ability, solid rebounding, and the ability to score on drives. This chart is on each slide is going to show the top 5 closest players to the cluster center point, and this chart will show the top 10 most important features in determining that cluster. So moving on to cluster 1, I call this cluster scores and multidimensional players. Key characteristics are simply scoring, very high usage, lots of touches, and I would go further to say just in general, just well-rounded players. Cluster 2 I titled as backup point guards. Some key characteristics for these players are high number of passes turn out to be assists, an above average number of dribbles per touch, and solid three-point shooting. They're well-rounded guards, but not quite good enough to be starting point guards. Cluster 3 I called athletic wings. There aren't many key characteristics to these players. I would say inefficient shooting would be the top ones. Cluster 4 I called dunk and defense post players. These players have the majority front court touches, high rebounding, good defense, and scoring within 10 to 15 feet. Cluster 5 are multi-dimensional role players. Some characteristics are good scoring, average number of rebounds and assists, multifaceted scoring, but they can tend to be inefficient. Cluster 6 I called the backup bigs. Majority front court touches, interior scoring, mostly dunks, and a high number of rebounds. Cluster 7 I called the skilled bigs. These guys have lots of touches, high scoring, mainly within 20 feet, and average to below average defense with a high number of assists for post players. Cluster 8 I called the 3 and D, but mostly 3. These guys play at a fast pace. They have great shooting. They're mainly scoring from behind the arc, and they have solid to slightly below average defense. And cluster 9 I called the stretch forwards. They have outside and inside scoring ability, high rebounding ability, and good shooting stats relative to other players in their position. So I'm definitely going to continue to work on this project and fine-tune it a little bit, and going forward I would consider not using any advanced stats and maybe even cut down on the traditional stats I use. And my reasoning for doing this goes back to the fact that these stats may tell us how well a player is playing, but not just how a player is playing. which I definitely noticed in the clusters in my project, because a lot of them seem to tell me the role a player played on a team and less of the play style, which is what I wanted. I would keep the shooting location data and touch data I have, and I would integrate some data that looks at passes a player makes, passes for an assist or just passes, who the player passes to, frequency of passes, etc. And also data that looks at how many dribbles a player takes, as well as how much they move over the course of a full game. This data over the advanced and traditional stats would allow me to better model simply how the player plays the game and the interactions that are common for certain players within the game. Once I have the clustering play styles fine-tuned, I'd like to work on a location aspect. I would have a visual representation of play styles based on a player's hometown. This, I think, would both be a very interesting and appealing visualization, as well as an informational one. So I'm definitely going to continue to work and fine-tune this project until I have a very accurate clustering algorithm working. And thank you for watching my presentation.